The following is a television production of the Space and Information Systems Division of North American Aviation.
Here at S&ID Seal Beach Manufacturing Facility, morning comes early. This is Pete Karras, 28 years old with 10 years experience as a metal fitting mechanic. His job here at Seal Beach is fitting, cleaning, and assembling prefabricated parts on the Saturn S-II. The man on the left is John Lewis, and the one on the right is Stan Cahoe. John is responsible for the electrical systems, and Stan checks out the instrumentation systems on the S-II. Together, they diagnose, locate, and correct problems in their particular systems and in combined systems. Meanwhile, the day shifts at the other facilities have begun. Here at Building 45 at Compton, Mildred Dwyer is already at work. Her task here involves the welding and building up of components and sub-assemblies which will become parts of deliverable GSE and airborne equipment for the Saturn S-II. In Downey, the test and checkout work is underway at the EMM. Here inside the EMM, a man named Bill Waldo is working on some of the equipment right now. At the Tulsa facility, lead man Joe Shin is already having his mid-morning coffee break. He and his men have been working in the fabrication of the S-II oxygen tank baffles all morning. While back at the Los Angeles division in Inglewood, California, in central manufacturing, men are operating machines which trim, size, and machine gores and waffle sections for the S-II common bulkhead. These men and women in widespread locations will work today and tomorrow as they did yesterday. They will work toward the completion of the Saturn S-II, the second stage of the largest rocket ever built by man. This is the total configuration of the Saturn V vehicle. And this is the S-II. It is 82 feet high, or approximately as tall as an 8-story building, with a diameter of 33 feet. Its particular mission is to launch the Apollo payload on its journey to the moon. Inside, the S-II looks something like this. A large cylinder capped at the upper end by a dome-shaped bulkhead. Now, this is the liquid hydrogen tank. At the bottom, the cylinder is closed by the common bulkhead, dividing the liquid hydrogen and liquid oxygen tanks. Here is the liquid oxygen tank. Now, it's formed by the common bulkhead and an aft bulkhead, which together make a pair of ellipsoidal structures. The liquid hydrogen tank wall supports the combined weight of the S-4B stage and the Apollo payload, consisting of the launch escape system, the Apollo command module, the service module, and the lunar excursion module adapter. 5 J2 engines provide the S-II with its thrust. Over 1 million pounds total. Enough energy to furnish electricity to a city with a population of 85,000 for 5 weeks. Well, that's what it is. Now let's take a look at how it's put together. Here at the top, this exploded view shows the forward skirt. Now, it's used to connect the S-II to the forward interstage assembly, which in turn connects the S-II to the S-IV-B. Now, below this are 6 cylinders, which make up the walls of the liquid hydrogen tank. And this is called the bolting ring. Now, mechanically, it's used to join the oxygen tank to the hydrogen tank and the thrust structure, which is below it. Now, the thrust structure and aft skirt assembly attach right here at the bolting ring. And the 5 engines are mounted to the thrust structure. A heat shield is installed around the engines to protect the thrust structure from the backblast of heat. And finally, the aft interstage subassembly completes it. Now, this part connects to the S-II, and rather connects the S-II to the S-1C, and it's jettisoned after the first stage separates. Now, if we break down this picture a little further, we get something like this. The forward skirt assembly attaches to the upper cylinder, or the number 6 cylinder of the hydrogen tank. Then there are 4 more cylinders before we reach the last cylinder, or the number 1 cylinder, which is welded to the common bulkhead and bolted to the bolting ring around the LOX tank. Now, in essence, you can see that the S-II consists of 2 large propellant tanks put together to form a large cylindrical structure. Now, offhand, it doesn't look like anything too difficult to handle, but with a series of boost stages the size of this, the relationship of one stage to another is critical. There's no room for mismatch of booster to booster center lines. To maintain thrust alignment and assure flight stability, it becomes necessary to hold tolerances to the smallest possible degree. Now, this means that the S-II must be built with the highest degree of precision and with a level of reliability never before achieved. These considerations make the job of each person involved in the building of the S-II critical and important. Similarly, the work done at each of the divisions and facilities is also critical and important. Briefly stated, these are the responsibilities assigned. Space and Information Systems, DOWNEY, is responsible for most of the engineering and tooling, and the Los Angeles division for most of the parts for the hydrogen and oxygen tanks. The TULSA facility is fabricating the interstage and thrust cone structures, the engine support assembly, and the oxygen tank baffles. While at El Toro, the explosive forming of bulkhead parts or gore segments is accomplished. And it's at Compton that the ground support equipment, the module assemblies, and the drawer and rack assemblies are being built. The Rocketdyne Division facility at Santa Susana will be the location of the static testing program. And here at the Seal Beach facility, the S-II is assembled and tested in all phases other than engine firing. This is the Seal Beach bulkhead fabrication building, as long as a football field, half as wide, and with an interior height of over 50 feet. It is in this building that the main structural components are fabricated, processed, and tested. These include the liquid hydrogen tank cylinders and the bulkheads. In addition, the thrust structure panels and the aft skirt panels are spliced together here, completing the thrust structure. These panels are fabricated at the TULSA facility. This is the vertical assembly and hydrostatic test building. It's 110 feet high and 154 feet wide. The structural components made in the bulkhead fabrication building are assembled here. There are 4 assembly stations, each big enough to hold a booster 33 feet in diameter and 80 feet high. On the east side of the building, there are 2 gigantic test stations, All hydrostatic tests will be performed here, plus the leak tests, tank calibration, tank cleaning, and LOX tank installations. This is the structural test tower where an early test article will be subjected to severe stress tests. It will be bent and twisted to make certain that the S-IIs will be strong enough to carry out their missions. This is the pneumatic test and paint and packaging building, where the S-II systems will be pressure tested for leaks, and also the completed S-II stage will be painted and packaged. The water condition plant seen here consists of two 600,000-gallon tanks and one 300,000-gallon tank. It is absolutely necessary for the insides of the liquid hydrogen and liquid oxygen tanks to be spotless. These tanks furnish a detergent solution used to clean the tanks and pure demineralized water to rinse them. In an emergency, they would also supply water for the fire department. This is the interior of the bulkhead fabrication building. Primary activities here are as follows: the fabrication of the forward, common, and aft bulkheads, the liquid hydrogen tank cylinders, and the assembly of the thrust structure and aft skirt. The liquid hydrogen tank forward bulkhead and the liquid oxygen tank aft bulkheads are each made up of 12 curved aluminum segments called gores, a ring centerpiece on some bulkheads called the dollar, and a bolt-on access cover. Assembly welding jigs are used to precisely locate the gores. They are then welded using a North American developed automatic skate welding technique. The fabrication of a single bulkhead requires a minimum of 300 feet of weld bead, which must be as perfect as possible. The welds are then inspected for voids by using X-rays. Following that, they are checked for leaks in a hydrostatic test and undergo a helium leak test. After the tests, an insulation layer is applied to the forward bulkhead. The process is as follows. The surface is first cleaned and primed. Then an adhesive material is applied. The insulation is then put on the prepared surface. It consists of nylon phenolic honeycomb filled with an isocyanate foam. This insulation is in turn covered with a tough plastic film. Then the assembly is cured in a large autoclave, thus forming the completed liquid hydrogen tank forward bulkhead. Now, this process is not necessary for the aft bulkhead of the LOX tank. The common bulkhead is a very intricate structure. It separates the hydrogen tank from the oxygen tank and must therefore form a perfect seal between these two highly reactive liquids, which also have an extreme difference in temperature. And yet this bulkhead itself must be very light in weight, while still being capable of supporting the weight of the liquid hydrogen, which is 157,000 pounds. Because of the extreme temperature difference between liquid hydrogen and oxygen, the common bulkhead is made of two separate bulkheads, the forward-facing sheet here and the aft-facing sheet here, which are separated by a thick layer of insulation sandwich. Now here is a sample piece of this insulation. It is a nylon phenolic honeycomb core and ranges in thickness from 4 3/4 inches to 80 thousandths of an inch. When the core has been placed on the aft facing of the common bulkhead, the assembly is covered with a vacuum membrane and moved to the 38-foot autoclave and cured. Later, the forward section or facing sheet is bonded to the core surface, again using the same technique. One of the more interesting aspects of bulkhead fabrication is the technique used to fabricate the gores of the common bulkhead. The gores of the aft-facing sheet of the common bulkhead and aft LOX tank bulkhead consist of a thick waffle section and a thin skin. It is at the LA division in Inglewood that the waffle sections are first machined out of aluminum alloy blanks. The partially finished gores are then taken to North American's El Toro facility, where they are clamped in mirror-finished female dies. Then they are placed in a tank of water and further formed by the explosion of an exactly placed charge of primacord. This forming procedure is repeated 3 times, and the gore is annealed after the first 2 explosions. After the final forming operation, the gores are returned to the Los Angeles division, where they are clamped in precision contour fixtures and heat aged to control and maintain dimensional stability. Finally, the skin thickness between the weld glands is reduced by chemical milling to eliminate weight. Throughout the entire procedure, progressive inspections ensure accuracy of trim lines, hole locations, and the maintenance of contours. Also produced in North American's Los Angeles division are the liquid hydrogen tank skin panel assemblies for the 6 cylindrical sections which comprise the tank wall. Each waffle panel of a section is made of an aluminum skin which varies in thickness. The variations in thickness are obtained by milling operations which produce a rectangular pattern of integral stiffeners. This is done by one of the world's largest 5-axis milling machines, operated by tape-programmed numerical control to maintain the consistent close tolerances required. Shaping the tank skin panel assemblies is done by brake forming. The panel moves slowly through the power brake dies. Deformation is pre-calculated to produce the final 16 1/2 foot radius for the panel. After inspection, the surfaces are cleaned and prepared. Then an adhesive primer is applied, and the panel is oven cured, following which the adhesive is put on. Then the honeycomb is checked over and, if necessary, reworked to make certain that it is filled with isocyanate foam. The panel is then covered with an adhesive bonded fiberglass and then oven cured. And finally, the insulation is bonded to the outside of the panel. The insulation is placed so as to leave the edges of the panel clear. After the panels are welded together to form the cylinders, these heat-affected zones will be strip sealed. Later, the internal subassemblies, webs, angles, and so on are installed on the machine's skin. After the insulation has been put on, the skin panels are vertically welded into cylindrical sections, and the frames are spliced together. Fabrication of the forward skirt structure, intermediate skirt, the thrust structure, and aft skirt is more or less conventional. That is, it's approximately like aircraft construction: riveted skin, stringer, and stiffener construction. Here in the vertical assembly building at Seal Beach, the final assembly of the S-II stage will take place. This is Station 1, where final assembly begins. It's the weld and trim station, where the cylinders are to be assembled, welded, trimmed, and X-rayed. This is how the liquid oxygen tank is put together. This is the common bulkhead, and this is the aft bulkhead, and they're jigged together and welded and checked for leaks. The completed assembly is then mated to the thrust structure by a bolting ring and an external bolting panel. Alignment is checked before the assembly operation is started and after it is completed. Next, the hydrogen tank cylinders are mated and welded. After assembly of each unit, the weld beads are completely X-rayed to make certain that they're up to specifications. Any unsatisfactory welds will be redone and rechecked. Then the forward hydrogen tank bulkhead assembly is positioned right here, above this last cylinder. It's trimmed, and when it's in perfect alignment, it's welded into place. This is followed by the installation of the forward skirt. And again, the closeout welds are X-rayed to make sure they're perfect. And this completes the structure. Then the stage will be moved into the vertical hydrostat station, where the hydrostatic or leak tests will be performed. And following these rigid tests, the S-II will be cleaned in one of industry's most unusual cleaning operations. Not only is the vehicle cleaned, but of special importance, every component to be installed within the LOX tank is also subjected to a thorough cleaning process. This is because of the extreme reactivity of liquid oxygen when combined with substances such as gasoline, some cutting oils and solvents. And in combination with liquid oxygen, they form a gel or jelly-like substance that is so sensitive it will explode if it is merely snapped by a fingernail. And while speaking of fingers, one of the most dangerous substances in combination with liquid oxygen is the natural oil left by fingerprints. As a result, every precaution is taken to ensure surgical cleanliness. First, components are cleaned in ethyl alcohol to remove grease and oil stains. Then they are rinsed in trichloroethylene. And finally, dried in hot, oil-free air. The tanks will be cleaned in several stages. The interiors will be vacuum cleaned and then wiped down with a detergent solution. Then, using a stainless steel boom with a rotating jet, a detergent solution under high pressure will be sprayed against the tank walls. Any foreign materials will wash out, and the tanks will then be rinsed. To make sure that everything is as clean as possible, the rinse water will be sampled and tested to verify that the contaminants are below specified minimums. Then the tanks will be dried with oil-free air at 120 degrees Fahrenheit. The next step is the installation of radial and annular plates and tank baffles in the liquid oxygen tank. The baffles will have been cleaned and packaged, and so will the plates. Then ultraviolet light will be used to check for contamination, and the tank will again be sprayed with trichloroethylene. The last inspection includes a leak check of the entire S-II stage. A mixture of air and helium will be put into the tanks at a pressure of 7 psig. Any leaks in the weldment will be detected by a helium detector, which is so sensitive that it will indicate 1 part helium in 10 million parts of air. This is Station 2 of the vertical assembly building, where all insulation closeouts are installed and cured and systems tunnel supports are installed. The stage is moved from station to station by means of stage dollies and this transfer table. After insulation closeout is accomplished, the stage is moved to Station 3 for systems installation. This includes the installation of hydraulic, pneumatic, and electrical components, including all connective tubing and wiring, and the 5 Rocketdyne J2 engines. Station 4 is the final stop in the assembly process. It is here that separate systems and integrated systems tests will be conducted. The flight of the Saturn must be supported by many items of ground support equipment, most of which are being fabricated at Compton. This is where you'll find Mrs. Dwyer in Department 568, working on GSE and airborne harness assemblies, some over 100 feet long. Boards are used in the manufacturing of wire harnesses, and automatic continuity checks are conducted here. Programming, patch boards, cable adapters, and matrix charts are certified by quality control. All soldering connections will be inspected for conformance to MSFC requirements. Modules for control, checkout, and servicing units are enclosed in standard consoles. Spares, modules, components, and purchased items are routed to a spares ready area immediately after completion of their functional tests. The number of accumulated spares and the hold period of each item is carefully controlled to maintain the hardware in a ready condition. Components that pass confidence tests during the receiving inspection process are then routed to the assembly area, where pneumatic, hydraulic, electrical, and electronic modules will be plumbed, wired, and installed to form a complete assembly. During the assembly process, as intermediate steps of assembly, wiring, tubing installation, and component assembly are accomplished, inspection personnel check and approve each major step. Upon completion, each drawer module assembly is subjected to a final inspection to assure that it is assembled to specifications and drawings. Final assembly includes the installation of wire harness like the one Mrs. Dwyer was working on, the tubing in the standard consoles, and the installation of electronic and pneumatic drawer modules in the console are also part of the final assembly operation. Cleanliness and care and handling are emphasized at all times during this operation. Each item of GSE is then tested again, this time functionally, to prove that it is compatible with the specific system for which it is designed. All devices are individually calibrated to standards established by the U.S. Bureau of Standards. The standard parameters of S&ID quality control and engineering specifications must also be met. Another North American Aviation Division which plays an important part in the development of the Saturn S-II is the Rocketdyne Division in Canoga Park. Here the J2 engines and various support equipment is manufactured. Rocketdyne supports the Saturn S-II program by providing test facilities and operations at the Propulsion Field Laboratory, Santa Susana. The supplementary facilities make the Santa Susana complex a complete self-contained propulsion test facility. Both the test vehicles being taken to Santa Susana and the flight hardware bound for Mississippi and eventually Mila, the Merritt Island launch area at Cape Kennedy, will be transported by water from the U.S. Navy docking facilities at Seal Beach. These facilities are approximately 1 mile from the assembly point. The S-II will be loaded onto a Navy AKD-1, which has been converted to carry the unusual cargo. Road gauge tests have already been conducted using a vehicle constructed to duplicate the dimensions and configuration of the S-II and transporter. After loading is accomplished, the AKD will be on its way toward the beginning of a history-making mission. A mission that was fashioned by the hands of Bill Waldo, Pete Karras, by Mildred Dwyer, John Lewis, Joe Schiff, and the thousands of other S-II personnel who have combined their skills and ambitions, hard work and devotion to create and build a reliable Saturn S-II. And in doing so, will also have contributed to man's greatest accomplishment, a successful lunar landing and return.
This has been a television production of the Space and Information Systems Division of North American Aviation.